Welcome back to Graph Theory. My plan today is to talk about paths in digraphs and graphs and tell you a few results I like with no particular system behind them other than me finding them nice. These are not mainstream results anymore like what we have done before. The first one, and the only one I will prove today, is the so-called Galai-Milgram theorem. And I'm following Distel's book here, which is pretty nice. So here is another theorem about paths in digraphs. First of all, some stupid definitions. Stupid because in a way we're just codifying something obvious. Two vertices U and V of a multi-digraph D are said to be adjacent if they are adjacent in the undirected graph, D undirected. So in other words, they are adjacent if and only if D has an arc with source U and target V, or vice versa. So source V and target U. Next, an independent set of a multi-digraph D means a subset S of the vertex set such that no two elements of S are adjacent. I mean, distinct. Well, it doesn't matter. No two elements are adjacent. In other words, it means an independent set of the undirected graph, D undirected. And finally, a path cover of a multi-digraph D means a set of paths of D such that each vertex of D is contained in exactly one of these paths. So note that we have already seen path covers of a complete simple digraph, so V cross V, in lecture 11. We called them path covers of V. So back then, path covers just depended on the vertex set. They didn't care about the digraph. Now we care about the digraphs. We want them to consist of paths of the digraph. So how does this path cover look like? Well, it's a path and another path and another path. And yes, paths can have length 1. They can have length 0, which means they have exactly one vertex. And these paths have to be disjoint because each vertex should be on exactly one of them. And they have to cover all the vertices. And note also that what is a path cover consisting of exactly one path? So let D be a digraph. A path cover of D consisting of only one path is the same as a Hamiltonian path of D. So to be more precisely, a single path P forms a path cover of D if and only if P is a Hamiltonian path. So this is a generalization of Hamiltonian path. Okay, and now we can state the Galai-Milgram theorem. Let D be a loopless digraph. Then there exists a path cover. Let me just call it P of D, and an independent set, let me call it S of D, such that each path, let me say it this way, such that S has exactly one vertex from each path in P. So in other words, for each path P in P, exactly one vertex of P belongs to S. So how does this look like? It roughly looks like this. Let me change the colors. It looks like you're picking one vertex from each pass. Here, from the empty one, you have, of course, to pick the only vertex. And the claim is that you can do this in such a way that they form an independent set. So you have no arc here, 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 no arc here. So if you had just two paths, it would be kind of simple, because for two paths you could pick, I think, what could you do? You could pick the end of one and the start of the other. If there was an arc, if there was an arc, actually no, it's not that simple. Because if there was an arc like this, you could of course combine the two paths, fine. But if there was an arc like this, what would you do? It's not obvious. So let's see how this can be proved in general. So first of all, a notation. If P, actually several notations. If P is a path cover of D, then a crosscut of P means a set S that contains, well, a subset S of V, and of course we write D as VA phi, so this V is a vertex set that contains exactly one vertex from each path in P. Okay, for now that's the only notation we need. So the claim is that there exists a path cover P of D and an independent crosscut of P. And I should say exists, not exists, because it's two things I'm claiming the existence of. Okay. So we will show something stronger. We will show that any minimum size path cover of D has an independent crosscut. So if you pick any minimum size path cover, you get an independent crosscut, so this existence follows. So note that the size of a path cover means the number of paths in it. So minimum size means as few paths as possible. So for example, if there is a Hamiltonian path, then you just take that. You should not be trying to, you should not be sloppy and like cut paths unnecessarily. Of course, if you have a Hamiltonian path, then this is obvious. You just pick a random vertex and that will be an independent set. The theorem is interesting when you have two or more paths in the path cover. Okay, but this is not the end of the totem pole again. We will show something even stronger. And I'm not doing this for fun. I'm doing this because actually the stronger claims are easier to prove. This is one of the wonders of induction, where if you make the theorem stronger, suddenly the induction becomes easier. So to state this stronger claim, we need more notations. First of all, if P is a path cover, then ends P means the set of all, well, the set of the ending points of all paths in P. So for example, how should I draw this way? Here are the ending points of the path in my path cover. So this blue diamond marked points, they form ends of P. Okay, I'm painting with such a broad brush that it's not clear what's actually in the set. Let me make this better. Right. So this is ends P. And the paths, I will soon give them names, but I don't need this so far. So note, of course, that the number of those ending points is the number of paths, because the paths have no vertices in common. Next, a path cover P is said to be end minimal if no proper subset of ends P can be written as ends Q for a path cover Q. So in other words, this is saying that I cannot have a smaller path cover with fewer paths, such that the endpoints of the path of the smaller path cover are also ending points of P. But of course, because the smaller one is smaller, at least one endpoint is not used. So for example, it means that if I restrict myself to those three vertices, they're not the ending points of a path cover. And also, if I restrict myself to those three vertices, again, I'm not being very clear, those three vertices, they're also not the ends of a path cover. So one obvious thing is that clearly any minimum size path cover of D is also end minimal, because if it wasn't end minimal, this Q would have smaller size than P. So otherwise, there would be a path cover Q with fewer ending points than P, and this means fewer paths than P. So the following claim is stronger than claim 1. The claim is that any end minimal path cover has an independent crosscut. Notice the word minimum versus minimal. This is a standard distinction in combinatorics. Minimum always means that some kind of numerical value is minimum, so some kind of numerical value is the smallest it can do. Here it's just the size. Whereas minimal means that you cannot remove anything from it. In this case, you cannot remove an ending point. So it is claim 2 that we will be proving. And how will we prove it? We induct on the number of vertices. Okay, the base case is obvious with 0 vertices. You have nothing to discuss. So what about the induction step? Consider a multi-digraph D equals VA phi with absolute value of V equals N, and assume that claim 2 is already proved for any multi-digraph with fewer than N vertices. Okay, and let P be an end minimal path cover of D. Let P1, P2, dot, 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 Pk be the path in P, and of course, no stupid things here listed without repetitions, so I'm not listing the same path twice. And let V1, dot, 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 Vk be the respective ending points. Okay, so let me draw this. This should be V1, except I should start further up. Yep, this is V1, this is V2, this is V3, and this is V4. And let me also label the paths. Can I label them bold-faced? Probably, but I don't know how. So think of the piece as being bold-faced. Okay, what next? So we want to find an independent crosscut of P. So first of all, if the set of the endpoints is not, so notice that of course these V's are the ending points, so their set is exactly the ends of P. Okay, so if the set of ends is independent, then we are done, because this set is clearly a crosscut. So without loss of generality, we assume that this is not the case. Hence, again, without loss of generality, there is an arc from V2 to V1. I mean, of course, there is an arc from some V to some V, but because the order doesn't matter, we can just reorder them so that the arc goes from V2 to V1. So I'm going to draw it. What can we do with this arc? So let V be the vertex that, okay, so first of all, if V1 is the only vertex on P1, so P1 is like P3, it would be a length 0 path. Then we can therefore replace the path P2 by P2 plus V1. So this sloppy notation means the path P2 with the green arc and the vertex V1 appended to it at the end. So basically you take P2 and you continue towards V1 and remove P1 from our path cover P, and we would thus obtain a smaller path cover Q such that ends Q is a proper subset of ends P. But this would contradict the assumption that P is ends minimal. So V1 is not the only vertex on P1. That was a bit of a degenerate case. The interesting cases come now. So let V be the second to last vertex on P1. So the vertex that is immediately followed by V1. Again, let me annotate this. This would just be V. It's visible, yep. Okay, what do we do now? Let D prime be the digraph D without V1. So in other words, the digraph obtained from D by removing the vertex V1 and all arcs that have V1 as source or target, or the induced subdigraph on the set V without V1. So let P1 prime be the result of removing V1 from the path P1. So in other words, V1 prime, you just remove the last vertex and the last arc from the first path. Then P1 prime, P2 ... Pk is a path cover of D prime. This is clear. If you remove this vertex V1 and remove it from the path as well, you get a path cover of the small bit digraph. So if we can find an independent crosscut of this path cover of D prime, then we will be done, because any such crosscut will also be an independent crosscut of our original path cover of D. So for original path cover P1, P2 ... Pk equals P. So basically, in this case, we get rid of this vertex V1 and have one vertex less. So how do we find such a crosscut? Well, we are in luck because D without V1 has one fewer vertex. So since the digraph D without V1 has n-1 vertices, we can find such an independent crosscut by our induction hypothesis if we can prove that this path cover, the new path cover, Actually, let me give it a name. Let me call it P prime. So P prime is P without this vertex V1. Let's see if I can draw this too. Almost. Drawing circles is tricky thing, but here it is. So this brown thing is D prime, and P prime is whatever remains of the path cover when we remove V1. So what do we need? We need to prove that it is end minimal. So let us prove this. Indeed, assume the contrary. Thus, D prime has a path cover Q prime such that ends Q prime is a proper subset of ends P prime. Consider this Q prime. Now, three cases possible. One case is if a path P in Q prime ends at V, then we can extend this path P by this one arc that we removed here, the arc, so by the arc V to V1, to obtain a path that ends at V1, and thus we obtain a path cover Q of D such that ends Q is a proper subset of ends P. But this contradicts the fact that P is, what was it, ends minimal. Okay, what next? If a path P in Q prime ends at V2, then we can extend this path P again by the arc V2 to V1, the green arc on the picture. So again, we obtain a path that ends at V1, and thus we obtain a path cover that's blah, blah, blah. So I should have said that because ends Q prime is a proper subset of P prime, and I should use a symbol for proper subset, which I always forget where to find it here. Remember that this ends are V1 and 2VM, Vk, so every path of Q prime has to end at one of the Vi's. So, except no, it's not V1, it's V, because we have cut off V1. So every path in Q prime ends at one of those, at either V or at V2 or at V3 and so on, or at Vk. Now we have found a contradiction whenever a path ends at V, and also whenever a path ends at V2. So the remaining case is if path in Q prime end neither at V nor at V2. So they have to end at V3, V4, and so on, Vk. So the remaining case is when each path P in Q prime ends at V3 or V4 or and so on, or Vk. In this case, of course, Q prime has at most K minus 2 paths. And now, adding the trivial path V1 to Q prime yields a path cover of D such that, let me call it Q, and again, such that ends Q is a proper subset of ends P. And this is again a contradiction to the ends minimality. So whatever option we take, we get a contradiction because we can extend the path cover of the Brown subgraph to the whole graph, and then we get its end set is still a subset of that of P. So we got a contradiction in each case, and thus we are done. We are done proving that our path cover P prime is end minimal. I think I should say end minimal, not ends minimal. Anyway, we got a contradiction, so the path cover is P prime is end minimal, so we can apply the induction hypothesis, so we can find an independent crosscut, and that's also an independent crosscut for the original digraph. Okay, this proves claim 2. As explained above, this completes the proof of the theorem. Okay, so what is so interesting about this theorem? Why could we want an independent crosscut? So why do we want to do this, basically? Well, here are two applications, and these are very simple applications. They can be done in a simpler way, as we have already done, but let me still give them just to give context to the theorem. So one is that, remember Reday's little theorem, which says that each tournament has a Hamiltonian pass. Well, this follows from Galai-Milgram. Indeed, the Galai-Milgram theorem shows that, let D be a tournament. The Galai-Milgram theorem shows that D has a pass cover with an independent crosscut. But since D is a tournament, any independent set of D has size less or equal to 1, because as soon as you pick two distinct vertices, one has to have an arc to the other, and that means they're not independent. So our pass cover must consist of one pass only. Otherwise, its independent crosscut would have size at least 2, and then it wouldn't be independent. But this means that its pass is a Hamiltonian pass. So D has a Hamiltonian pass.